Hello everyone, my name is CSAC Ponduru. I'm a PhD candidate at Missouri S&T under Dr. Aditya Kumar in Material Science and Engineering Department. Today I'm going to present on the effects of flash on the properties of calcium aluminate binders. So we know that as the infrastructure is growing up, we have ordinary Portland cement demands increasing, and we know that it contributes to around 8% of CO2 emissions globally. So there is an urgent need for the alternative binders. If you look at the figure, if you take a gram to gram per basis, ordinary Portland cement emits around 100% of CO2 emissions, whereas calcium aluminate cements only emits for 53%, which means that CAC is sustainable compared to OPC. CAC, also known as calcium aluminate cements and high alumina cements, were originally developed by Lafarge in 1909. The raw materials for CAC are limestone and bauxite. Even though CAC has limestone as one of the raw material, the percent mass when compared to OPC is way lesser. It's around 30% to 40%. And the calcination temperature for CACs are around 1200 degrees, which is less than OPC, which is 1450 degrees Celsius. The major phases are Ca and Ca2. Now, we know that calcium aluminate cements are sustainable, but how can we make them more sustainable? So by introducing SCMs, we can make them more sustainable. In our research, we have considered, there are a lot of SCMs like limestone, metakaolin, flash, slag, but we considered flash because the flash is one of the most utilized material in the infrastructure industry, and flash is a coal combustion byproduct, and it is classified as class C and class F based on the lime content that is present. The chemistry of flash significantly affects the hydration and mechanical properties, one through Pozzolanic reaction in ordinary Portland cement systems, where the silicate ions react with calcium hydroxide to form CSH. The other one is filler effect, where it provides additional surfaces for heterogeneous nucleation and growth. The sulfur content in the fly ash might affect the system, the hydration properties, and the mechanical properties, either by forming ettringite or slowly converting to monosulfoaluminate. Due to the coal source, the combustion technology, cooling techniques, and the catching techniques, there is a batch-to-batch variation in the chemical composition of flash. Now, we know that we are using flash, but is there a standardized method to estimate the reactivity of flashes? For ordinary Portland cement systems, we use Chappell, Fretney's, and R3 test, but if we have like 10 to 15 flashes, is it viable to do all those tests? So that's why we bring in a concept called topological constraint theory. So this theory basically talks about how a microscopic changes within a system can affect the macroscopic properties. The topological constraint theory consists of two parameters called network formers and network modifiers. The network formers are Si and Al atoms, whereas network modifiers are alkali metals. The more network formers you have, the structure will be rigid. The more network modifiers you have, your structure will be weak. Now, since these are applicable to calcium alumina silicates, we can apply them to flashes. Now, flash composition has different oxides. That is the reason why the topological constraint theory reduces the complexity to bring in a single parameter called number of constraints. And the number of constraints is calculated based on the mole fractions of lime, silica, and alumina content. And this can be used as a proxy for the reactivity of fly ashes. The higher number of constraints you have, the higher rigidity, which means the lower reactivity. The lower number of constraints you have, which means the lower rigidity and higher reactivity. So in our research, we used 13 unique fly ashes with varying chemical compositions. We replaced the CAC between 10 to 50% at 10% intervals with a constant liquid to solid ratio of 0.5. We used isothermal microcalorimeter to measure the heat release. Compressive strength was measured for all the CAC plus FA binders using ASTM standard C109. For analysis of phase assemblage, we used X-ray diffraction and thermodynamic modeling. and we used a software called Gibbs energy minimization software. Now, before going further on how CAC plus FA binders behave, we need to know the basics of CAC hydration. The products of CAC hydration are calcium aluminate hydrates and calcium aluminate silicate hydrates. There are certain parameters that affect the calcium aluminate cements hydration. First one, composition. Let's say you have an anhydrous phase of Ca higher than Ca2, then you have more amount of hydration products being formed at the early hours. If you have more Ca2, then you have less amount of hydration products. Water to cement ratio, the more amount of water you have, you might have free water. The less water you have, then you have anhydrous phases not reacting. Other thing is additives. Let's say if we add gypsum, then there is a possibility of ettringite formation, which can slowly transform to monosulfoaluminate. This might affect the hydration kinetics and the mechanical properties. And the last one is temperature dependent. Now, if you look at the figure, so at 5 degrees, you can see that more amount of CaH10 is being produced, whereas at 23 degrees, you can see that C2AH8 is being produced along with gibbsite. So the content of metastable phase CaH10 is reduced. At 40, you can see the stable phase, which is gibbsite and hydrogarnet. So we know that as the temperature is increasing, the hydrate phases are being affected. Now, like I said, we use 13 different flashes. Flash 1 to 6 are highly reactive flashes. So what's happening in the high reactive flashes is, since the NC is lowered, you have more amount of silicate ions being released, and the silicate ions react with the anhydrous phases or the hydrate phases to form stratlingite. And it has higher cumulative heat and greater strength. Now, if you look at the cumulative heat profiles, all the profiles has higher cumulative heat when compared to plain CAC cement. Now, in low reactivity flashes, it's completely the opposite. Since we don't have enough silicate ions for the anhydrous phases to react, the flashes are basically acting like filler effect. So they are providing additional surfaces for them to form more calcium aluminate hydrates. Now, if you look at flash 8 and flash 11, both of them have higher heat flow, but flash 8 has lower induction period compared to flash 11. This is observed because the flash 11 has sulfur content, and which is around 2%. And if you look at flash 7, it has higher amount of sulfur content, which is 4%. So that is the reason why we believe that the sulfur content is one of the things that might affect your CAC hydration. Now, we showed how the silicate ions are being released, how the heat flow is affecting. Now, so in order to experimentally prove whether our thesis is correct or wrong, you can see that plain CAC, now you can see CaH10 being formed, but you can have anhydrous phases like Ca and Ca2, which means even after 3 days, you still have some amount of CAC which is unreacted. Now, flash 3, we took 50% replacement. This is just representative of the low reactive flashes. Now, you can see that you have more amount of stratlingite being formed, which means that more amount of silicate ions are being released for high reactivity flashes. And flash 7, which is low reactive flash, you can see that very less amount of stratlingite is being formed. This proves the TCT theory that the higher NC you have, the lower reactivity, and the lower NC you have, the higher reactivity. Now, we did thermodynamic phase assemblage to see how the reactivity of flashes are affecting the hydration process. So for plain CAC, you can see at 79% we had a dashed line. So this is the degree of hydration of plain CAC at 3 days. We calculated this by taking the ratio of cumulative heat of CAC at 3 days to 21 days. At 87%, you can see that there is no water left, which shows that the hydration has been arrested because of less water. Now, as we said before, flash 3, you can see more amount of stratlingite being formed, compared to flash 7, which has only less amount of straddling gate is forming. Now, we have the thermodynamic phase assemblage, and in ordinary Portland systems, usually we try to compare the volume fraction of hydrates versus compressive strength. And if you get a linear fit, then it is called as the crude measure between solid-solid connectivity. We tried the same thing for CAC and CAC plus FA binders. We got a linear plot. Now what we have done is we have considered plus or minus 5% the points of flash reactivity that are passing through, and plus or minus 5% of the line. Now, in GEM simulation, when we give the input of flash to be 10%, GEMS assumes that all the 10% is reacting. So you need to restrict the flash reactivity. So that is why we have chosen the flash reactivity to be between 1 to 30%. And we have only did selection of certain hydrates, which is like CaH10, C2H8, and stratlingite, because those are the phases that provides strength in the CAC cement. So once we did all that, we took the average of all the reactivities at different replacement levels. And one thing we found is, independent of the replacement level, we have the same reactivity for a certain flash with certain composition. And we observed that as the number of constraints are increasing, the flash reactivity is decreasing. The flash reactivity we observed are between 4 to 26%. And the conclusions are, if you have high NC, then it has a low intrinsic dissolution rate, which means it has lower potential to react with CAC phases, which eventually means that lower cumulative heat and compressive strength. Whereas for low NC, it's completely opposite, because you have high amount of or sufficient amount of silicate ions being released to react with anhydrate phases and hydrate phases to form stratlingite and other components. From the thermodynamic phase assemblage and XRD, we clearly showed how it has a good correlation with the TCT theory. And finally, we would like to say that the degree of reaction of flash is independent of the percent or the replacement level. And as the NC is increasing, the flash reactivity is decreasing. The scope of this research is, if a person is given 15 to 20 flashes, in order to know the flash reactivity, you have to perform a lot of experimental tests. So our research at least gives you an idea whether the flash is reactive or not reactive based on just the XRF composition, even without performing any experiments. We'd like to thank the Missouri SNT and the Materials Research Center at Missouri SNT and NSF for their financial support. Thank you.